It was basically yesterday, I think was the first time I had not taken a photo of myself. Didn't last, thank you. Okay, so this topic, first and second derivative, we're looking at just more differentiation. You'll find that the differentiation itself is mostly easier than what we've just done in that previous topic. So that's really where we're looking at just differentiating, where we can do some tricky things and we're not really doing much with it, okay? But we will still differentiate those things and do things with them, if that makes sense, just not the super difficult questions that we were looking at. Our focus here is differentiating so that we can draw more complicated graphs than what we've been drawing before. So we'll use differentiation to find turning points, okay? So our maximum or minimum points. So we'll look at the first derivative being the gradient, which we've already talked about, and then the second derivative will tell us the concavity, which we'll look at, but this is concave down because the arrows are facing down, and concave up. But remember that you're going to have graphs that have changes in concavity as well. So like there's somewhere along here where this graph changes from being concave down to concave up, okay, and that would be called a point of inflection, but we'll talk about those.
Can we steal that extra chair because we are short on chairs next door?
You may. And there's also, you feel free. You have a starring role in our video now. Quality. Feel free to wave to the camera. Okay. So, I think we've remembered this well when we differentiate. We're finding, am I using the old pen that Darren did not just bring me? I think so. I threw you in the bin. Okay. So, we're finding the gradient of the tangent to the curve. So, remember the gradient is showing us the slope to 25 degrees. Oh no, wait, wrong button. It's okay. Crash is subverted.
Did you make that one?
No, I wrote that. Okay, so you can see here that at this point P, that is the tangent to the curve, and when we differentiate and sub in that x value of P, we're finding the gradient of this line, okay? Now, we've talked before about what happens here. What happens? The gradient is 0 at a turning point, okay? We'll focus on that quite a bit in this topic. Another thing to remember, what do you know about the normal?
Perpendicular.
It's perpendicular to the tangent. Okay, so remember that the gradients multiply to give -1, okay? But if one of the gradients is 3, how do you get the other one quite easily? Yeah, flip and make negative. Okay, so Brian is whispering -1 over 3. So flip and make negative. This is the way I would think of it when I'm just finding the gradient of a perpendicular line, okay? Whereas if I was asked to prove that two lines are perpendicular, that's when I'd be more inclined to show that the two gradients multiply to give -1. So it's nice for a proof, let's say. You can fill it in the bubble that is on the slide. Yeah. Okay. I hope we're okay with this one, right? This one? The same. No gradient, 0, you could say. Or, well, like, if you had a vertical line, we'd call that undefined, the gradient. Okay. So, we've done this before. Where is it? 0. When is the curve increasing? And when is it decreasing? You can do that on the next slide as well. Okay, so you can see that the gradient is changing. Okay. When is the curve increasing? Okay, so as in the gradients of 0. So between the turning points. How did you know it's increasing then? Because it's going up. So the gradient is positive. Okay. So increasing is when the gradient is positive, okay? Decreasing is when the gradient is negative, and stationary is when the gradient is
0.
Okay, so we call these stationary points, okay? Okay, have you already done this for those two graphs? Wonderful. What do you notice about these two graphs? So we've got here, well, can you tell me what type of graph this is? An exponential and a cubic? What can you tell me about these graphs? Benj?
The first one's increasing at an increasing rate.
Oh, yes. Okay, so it's increasing at an increasing rate. And this one is not increasing at an increasing rate at all times because it flattens out, but it's always increasing, right? We do have a stationary point here, which we've talked about a number of times, right? So this is what we call a horizontal point of inflection. So you might remember before, don't be stressed, we'll talk about it again. A point of inflection is where concavity changes, okay? So in, for example, your tan graph, concavity changes, yeah? But we don't have a horizontal point of inflection, it's just a point of inflection where the concavity changes. It was concave down, now it's concave up. Whereas here, can you see the curve really flattens out? If we drew a tangent there, it's Jamila, if we drew a tangent there, it would be flat, right? So we have a gradient of 0 there, so it's different. Okay, I really like that kind of feedback, thanks. Now, we call these monotonic increasing.
That sounds like
So they're always increasing, which we've talked about before. But if you were told the curve is monotonic increasing, it means the gradient is never negative, actually. Yes.
jump up.
Maybe?
Or like just turn the fan down a bit. Really like flowy. Wow.
I'll turn it off for a bit, and then we'll put it back on when we're cutting it. Okay. All right, team, come on. So, have a look at this question. I would like for you to go and have a go at this. So note that you have an equation there, okay? So when you're completing the, well, when you're finding dividend, it's obviously going to use that, but when you're completing your table of values, you're subbing into the equation. That's for dy on dx, so that's, remember, the gradient. we sub the x value into the derivative, so into the gradient. So you're finding a table of values for the gradient. Okay, now we expected this one because we know a parabola is symmetrical, so the turning point is going to be halfway through the roots or the x-intercepts. So we know that that's at x equals 2. We know the gradient is 0 there. Now this one, previously we've drawn the graph of the derivative on here, but without equations, right? Where we've just looked at, okay, when is it 0, where is it positive, where is it negative? And it's somewhat inaccurate, but we get the idea of it. Whereas here, we can draw it quite accurately. Although, it's helpful to remember, if your diagram is a parabola, the derivative is going to look like a straight line. Because when you differentiate a parabola, you get a straight line. You go from a quadratic to a power of 1 for x, which is linear. If you had a cubic, then you'd expect a parabola as your gradient curve. So it's helpful to know what to expect, even if you don't have the equation. Okay, so you will need to actually get a bit of a scale going on your y-axis because you do have the equation, so there needs to be some accuracy here. We actually know where that turning point is, so how high up is the turning point and how do you know? So where's it turning around? X is 2, how do you know what y is when it's turning around? Yeah, just put it in the equation. Which equation? The original, because it's on the original graph, okay? So the original equation is this, at x equals 2, y is 4. Okay, sorry if that's not quite in line, it's hard for me to get that high, and I can't see. Parallax error, that's cool. I think it's a little bit low. So that's actually my y-intercept then, isn't it? For 4 minus 2x. And honestly, I'm not going to plot all those points. I'm just going to plot the 4 and the 0, and then I'm going to rule my straight line. I only need 2 points. 3 is good as a backup, but I'm confident that they're accurate. And I've chosen the key points to make sure that they're right, because remember our intercepts are important. If you draw a line, and you miss the intercept, you need to correct that, okay? It's something that we look for as we mark. Now, apologies because I don't have my ruler in this room, so let's see. Oh, that wasn't too bad. Now, I'm kind of thinking here, as I draw this, sorry that it's a little bit wobbly. What else am I thinking as I draw that line? So I thought I need to get the intercepts correct. What else am I thinking I need to be careful of that now I'm like, sure, arrows. Yeah, so I'm thinking about 2 graphs' point of intersection, whether that's important. So I'm concluding here, look, that's not really our goal, but if you are drawing 2 graphs together, then you need to be mindful of the point of intersection and make it accurate, okay? So that would just be solving simultaneously, which we want to do for this situation. Okay, so we've drawn the graph, and yes, we can have arrows. I would extend that. I've just run out of board. Okay. So So, for what values of x is the derivative bigger than 0? What does that mean? How do we interpret the derivative bigger than 0? Derivative means the same as
Both the,
not y, y dash, which is the same as the m, just m. Okay, let's try this again. Okay, so what's dy on dx that we're looking for?
The gradient.
Oh, good job, everyone. Okay. So, but it is really important that you want to remember the derivative is finding the gradient. Okay, especially when we're thinking graphically. So the gradient is positive. You don't need to investigate this table of values to know when the gradient's positive. You can see on the graph, it's positive up until x is 2, right? That's all that we're being asked, but it feels more complicated, right? So how are we going to write this? When is the gradient bigger than 0, yeah?
When x.
Beautiful. When x is less than 2. Can it be equal to 2? No. When is the gradient 0? Okay, at x is 2. Now, can you see that this is the case on our gradient graph as well? You can see that the gradient is positive until we get to 2, and then the gradient is 0, and then it's negative. But we can see that on the line here. So this is drawing where the gradient is your y-axis. So the y-axis becomes an m-axis, essentially. Okay? It does become a little bit confusing, I realize. So this one is when x is bigger than 2. Okay, we have a negative gradient. So really important, first derivative means gradients. Okay, particularly when we're thinking about pictures, graphs. Describe the function where the gradient is bigger than 0. Well, let's use the words that we were talking about before. When the gradient is 0, we say that the graph is
Monotonic
I'm not in the video now, so no one can see that I'm making signs. Not monotonic increasing. So I thought I was funny. Monotonic increasing is for the whole graph. Okay? So it's just increasing. So when the gradient is positive, we're increasing. Okay? When the first derivative is negative, the graph is decreasing. Okay? So I want you to think to yourself, first derivative, I want you to think gradient. Well, I've already drawn on myself this morning. So. Thank you for laughing at my misfortune, kind
lot.
Oh, the pregnant woman dropped something and has to bend down and pick it up. Yes, okay. Actually, last time that I was quite pregnant, someone like dropped something off their desk onto the floor and was like, "Oh, can you pick that up for me?" And I was just like, "Really?" Like, even now, like, it's definitely harder to go down. All right. So, yes, it's all about the squat. Yep, you gotta practice. It's a good pregnancy exercise and other exercise as well. Okay, everyone, keep fit. We should cut this out of the video. Okay. What happens when the first derivative is 0?
It's stationary.
Okay, we say it's stationary. So that's your turning point. Okay. I think I left this slide to complete that question, but that was not necessary. So. I'll put it back on again. Don't you do it, Rachel.
Yeah, Rachel.
Take your blazer and put it back on.
Okay. So let's mark the gradient, the plus minus 0 on this curve. equation have we seen? Okay, y dash dy on dx. M. Okay, I'm going to write x dot, but just note that normally that's when we're in terms of t. Yeah, but that's our first derivative as well. And maybe the worded version. Oh yeah, derivative. That wasn't actually what I was thinking. Oh no. It's not a derivative. Somehow I feel like things have gone downhill for me. The long one. That's a key thing that tells us to differentiate. Gradient of the tangent to the curve, okay? So we have to know all of these things. I know, but you all came up with them, right? So it's things that we've been changing between. I don't think you have any problem with that. But it's really, really helpful when you're thinking about graphs to see y dash or f dash of x and think gradient. Okay, because it helps to get your mind in that right frame. Okay, so hopefully you've already done this. Okay, and so this is just...
What about like rate of?
Oh, yes, I love that. Okay, so maybe we say rate of change. That's a great one. Rate is a really good clue that you need to differentiate. Yeah. All right, so we said when f dash of x is positive, the curve is doing what? Increasing. Because that's a positive gradient. When it's negative, it's decreasing. And when it's equal to 0, Tim, if you're talking but not contributing to what we're doing, you're actually doing the wrong thing and disrupting us. Okay, so when f dash of x is equal to 0, it's the turning point, so we say that it's stationary. And we call it a stationary point or a turning point. Okay, maybe a vertex. Okay, so that's really the key that we're looking at this lesson. That stationary, increasing, and decreasing, what that means for a derivative and a gradient. Okay, so have a look at this next question and see how you go. Ainsley. So you can't see that very well. The increasing was the bigger than 0. It's the same as from the last slide, but we've put in the inequality. Okay, that's right. There's no graph, but you know how to find the gradient. How do you find the gradient? Okay, so if you're asked about a stationary point, you're going to be asked about stationary points a lot. Okay, that means differentiate. If you want to know about a curve increasing or decreasing, that's talking about the gradient of the curve. If you don't have a graph, then differentiate. Okay? If in doubt, just differentiate. No, jokes. Okay, so tell me, how are we going to find where this curve is stationary?
Equate it to 0.
Okay, so we want the gradient to equal 0. Okay, now, we do need to be careful with these questions, okay, where sometimes it asks for a point, the stationary point. How would that be different from my answer here?
You need the y value.
You would need the y value, okay, and that would just be subbing into the original equation. Now, can you tell me, if we didn't know how to differentiate, how would you have found the vertex? Yeah, x equals minus b on 2a, which is 4 on, hey, right, same. But having said that, we're going to look further. So we're going to look at curves other than parabolas, okay? Whereas we don't have that strategy for anything more complicated than a parabola. So when it's increasing, the gradient is positive. So I'm looking for 2x minus 4 to be positive. Does that seem okay? And we're solving an inequality. Just a reminder, inequalities are exactly the same as regular equations, with the exception, simple inequalities, okay? Extension, we've looked at harder ones, different. When we solve simple inequalities, same rules, except if we multiply or divide by a negative, then we flip the sign, okay? We're not going to have to do that here. And then this one here, I mean, this one here, do we really even need to solve? I mean, it's exactly the same, but with the sign flip. So it's going to be that x is less than 2, right? But you could solve. Okay, so as I've mentioned, we will be using stationary points to help us graph curves. That's kind of the key of this topic. Okay, have a look at the next one. This one is a bit trickier. Actually, we probably need to talk a little bit about how to solve this, to be honest. It's a bit of a shame that we used to actually look at solving inequalities and quadratic inequalities in advanced. We have done that in extension, but it's quite useful for a lot of things we do. So we'll have a little look at that. Shouldn't be a problem here. So if you are asked to find a stationary point, if you're talking about a curve increasing or decreasing, that's talking about the gradient of the curve. The gradient of the curve is the derivative. So you want to differentiate and solve that to give whatever gradient you're after. Do you need to go and step outside to calm down a bit? Okay. Okay, so the gradient is, I will usually try to write m equals when I'm thinking graphically because it helps me to be in that frame of mind. I want it to be equal to 0. Now, before we go solving this, what's going to make this much easier for us? Divide both sides by 6, okay? Now, remember, we can only do that because it's an equation. If it weren't equal to something, we could factorize and take out the 6 and then continue to factorize. But we can only do this because we have two sides. Okay, and then this is much easier for us to factorize. So what you will find, so in advance we've looked at like this that are cubics and they're bumpy. We haven't so much looked at them in advance, but a cubic, instead of looking like our normal cubic, okay, when you've got these extra x squared and x terms in between, what that will often do is make it a bit bumpier, okay, something like this. And so, can you see how we found 2 stationary points? That's because it's bumping around like that, okay? So, just checking, it says find the x values, not the point, okay? We want to watch out for that. If it says point, make sure you find the y value, okay? Now we want to look at when this is increasing. Okay, so this is where it's a little bit trickier. So we're looking to solve a quadratic inequality. Now, the way we do this, well, there are a few methods that you can use, but the way that I like to use is a graphical method where we basically draw a pretty dodgy graph of this parabola. Now remember, we've already factorized that, so we know that the roots of the parabola are -1 and 4. Are we okay with that? And it's an x squared, so it's a happy face parabola, a concave up parabola, so it looks like this. That's the only other bit of information you need. Is it concave up or concave down once you've got the roots? Okay? Now, we're looking for this, which is equivalent to y. If this is my y-axis, would you agree with that? That would be y equals x squared minus 3x minus 4. I want y to be bigger than 0. Okay? Now, where is y bigger than 0? Up. Oh, yeah, sorry. I was meaning more generally, but yes, thank you. So, up above the x-axis. Are we okay with that? This is all the positive y values. Like you'd have 1, 2, 3, and it would keep going. Yeah, positive. Y would be less than 0 down here. All the negative y values, etc. I don't know what that point is, don't care. Okay? And where is y equal to 0? Right here on the x-axis, which is our values that we got when we solved it equal to 0. So, Jamila and Luke did answer this question. Where is y bigger than 0? In, oh my goodness. And now it's like this room is trapping me with the thing that's like, I got it, go, okay, go. Squat action 2. I don't know if I should be concerned that I'm getting collapsed for picking up a pen. Low expectations. Alright, so we're looking at those parts of the graph. Does that make sense? The parts that are in the positive y values above the x-axis. So this is to the left of -1, so that's when x is smaller than -1. And to the right of 4, so when x is bigger than 4. Okay? So that will be when our curve is increasing. So what you'll find is that this is x equals -1, and this is x equals 4, and you can see it's increasing, and it's increasing, and you can see in between it's decreasing as well, okay? But where it's confusing that we're interpreting it from a parabola, because this is the gradient graph, when the real graph is a cubic. So here we're looking at the slope, it's positive, it's negative, it's positive. Here, we're looking at the y value. It's bigger than 0 is above the x-axis. It's quite confusing to get your head around that, okay? Because that y is really our m here, okay? Now, when it's decreasing, we're solving this to be less than 0. It's the same graph, so I'm not going to redraw it. Thanks, Dean. And so where is it less than 0? That's looking at underneath, and that's between -1 and 4. Now, how do we write between? X in the middle. And then what? Less than, less than. Okay, so less than. It's less than 4, but it's bigger than -1. Look, if you get really stressed about it, then you can just go, it's that way of -1, so it's bigger than -1, and it's less than 4. That's acceptable, okay? I mean, this is better, isn't it? Because this one is not between. It's 2 separate sections, whereas this one is in between. Okay? Okay, last one. Use a pencil because it's a graph. Start drawing it and then see if you maybe need to tweak some things as you go. So draw yourself an axis, or a number plane rather, axes. Oh well, I didn't try to draw it first, so hopefully I didn't start with it. I hope it makes sense. I got something the wrong way around. Which bit do you think is?
Because it's like, yeah, well, not ways negative, but it's right?
And that doesn't fit with the original values, is that what you mean? Or?
No, it's just a descriptive.
Oh, okay, let me have a think about it then. We're going to try and draw it. So I would of course rule my axes. I don't have a ruler in this room, unfortunately. We should be back in our normal room next week on Tuesday, I think. We're back in. HSC finishes on Monday. So f of 3 is 2. That's just like saying the point 32 is on this graph, right? F of x, so x is 3, okay, and f of x is equal to y, so 2 is your y.
restrictions or swap?
So I'm going to have to tweak. Oh, what? If I make it so. So if I switch
And then it's positive. The whole expression doesn't make sense. Well, unless you do it. But it positive the whole way.
Sorry, I'm going to just have to tweak because you actually can't draw that. Sorry. Okay. Let's see if this works. If we switch those around. Oh, is that going to work now?
What did you change?
Which we could have then, I could have just said from -1 on it because it's 0. Well, we don't actually know what f dash is at -1, so maybe. Okay, so you'll have to try, sorry, with this swapped around. Sorry about that. Okay, so you know with the, I just can't read it. Oh, why is that all changed? Anyway. So you know that if f dash of 3 is 0, what does that tell you? Okay, so that's a turning point. So f dash of 3 is a turning point here, okay? And then you know f of -1 is 4. Or maybe if I'd made that -4, would that have worked? I think that might have been my typo, but it was supposed to be -4. First, do you want to see if that would work? If it was -4 but the original restrictions? So I had it exactly the same, but that was equal to -4. Would we be able to get that to work better? Well, that's what I've done. Like this. I've swapped the restrictions, but I think if I'd done that as -4, it would have worked. Yeah? Okay, so the gradient is negative over here. So that means the graph is going down. Yeah? Something like this. Yeah? That's a negative gradient. So it feels maybe wrong, boys, that it's up high because you think of that as big and positive, right? And it is, but a negative gradient can be anywhere. It just has to be heading downhill, okay? Now, apologies for the, I think I made a different typo, but anyway, we've sorted it out so you can draw it. So then it continues to be negative. We don't know at -1, which means, boys, again, I'm asking for you to be quiet. It could be a stationary point here or maybe not, okay? And so it just continues down, and then here we have our turning point, and then the gradient is positive. So maybe it looks something like this. Doesn't have to look exactly the same as mine. Camilla?
Why doesn't -1 not have that?
It's because I think I meant to have a -4 here, so I had to tweak the question. Yeah, so it wasn't quite supposed to look like this, sorry. But it just means that you don't know if that's a stationary point or not. That's all it means. So it's either going to be a negative gradient or a zero gradient. Okay, so you've got that exercise. Make sure you're up to date with your homework. If you have not redone your exam, please do that. It's a really important